LearningMeasure.tv, science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 4, Near Field Antenna Measurement. Hello. Welcome to episode 4 of the LearningMeasure.tv podcast. I'm David Archer. This is my deal. This episode, we have two sponsors, GoToMeeting.com and TradePub.com. Last week we talked about a particular application of wave phenomenon, measurements of wave phenomenon, and that is the near field measurement techniques. We're going to go over that in detail in a minute, but first we're going to have a little bit of a review. Okay, we just went over last week, or in past 2 weeks, that the general form of a plane wave is e to the I k dot r, where k, remember, is the magnitude of k equals omega over c, and k itself can be written as a omega over c times a unit vector in the direction the wave is propagating. Okay, and we're going to talk a little bit more about that in a second, but let's talk about vectors in general again. Okay. Here we've got a three-dimensional coordinate system, three axes. We'll call this x-axis, y-axis, z-axis. A general vector that's represented by an arrow is characterized by three numbers, x, y, and z, components, I guess. So each number is the projection into an axis. So this is the right angle here. This is z, x, and y, coordinates of the vector. Okay, there's also something called spherical coordinates that you can describe a vector by, where its length is r, and the angle between the z-axis and the vector is called theta, and the angle between the x-axis and the projection into the xy plane of the vector, which this is r, is that angle here is called phi. So you've got two types of coordinates. You've got Cartesian coordinates, which are x, y, and z to describe a point in space, and polar coordinates r, theta, and phi. Okay. From this drawing, you can see this is a right triangle. You know r and z and theta from trig. You can deduce that z is r cosine theta. Well, from trig, you got yourself a right triangle here. You know it. Well, anyway, you know this triangle, so you know this is r sine theta. So the projection of that into the x-axis is r sine theta cosine phi. So we've got x equals r sine theta cosine phi, and y is r sine theta sine phi. Okay, so those are just two ways of describing a vector. Okay, and this is the relationship between the spherical coordinates and the Cartesian coordinates. Well, imagine r equals 1. So that you have a unit vector. So we have the general unit vector, let's say k hat, is equal to kxx plus kx x hat, unit vector in the x direction, plus ky y hat, unit vector in the y direction, plus kz z hat, unit vector in the z direction, or using these relationships, it's equal to magnitude of k times sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. Well, we already know magnitude of k is omega over c. So we can now go back and forth between spherical and Cartesian coordinates, and we know we can write this general plane wave now. Let's keep some of this. General plane wave, then, which also is equal to e to the I k, magnitude of k times k hat dot r, which in this case we know is e to the I omega over c, or 2 pi over lambda, or whatever expression you want to use, k hat dot r, where k hat is the direction now, represents the direction the wave is going. Or in general, the plane wave is some amplitude times e to the I omega over c k hat dot r. Okay. Well, now we'll go back to the concept of localized object emitting some sort of wave, electromagnetic wave, acoustic wave, some sort of wave. We already shown last week that as you get far from a localized source, the waves look like plane waves with a particular amplitude in each direction, which now we can write as a of k hat, some amplitude that's a function of the direction the wave's going, times e to the I omega over c k hat dot r, which of course equals a of k hat e to the I omega over c kx x plus ky y plus kz z. Okay. This is, in antennas, it's called the antenna pattern. You might call it that for speaker too. Maybe call it a speaker pattern. I don't know. But this gives you an amplitude of plane waves in the far field. This can also be written in terms of theta and phi. Now that we know k hat in terms of theta and phi, it's this thing here. So we can also say this is e to the a theta phi, a function of theta and phi, times e to the I omega over c k hat of theta and phi dot r. Okay. That's just the basic mathematics of plane waves and far field patterns away from a localized source. And now to pay some bills. Do you spend more time traveling to meetings than you do actually meeting with people? If your time is valuable, and whose isn't, then you need GoToMeeting. With GoToMeeting, you can instantly meet with anyone. All you need is a PC and an internet connection. During the meeting, your attendees see that on their computers what you show on your PC. It's like you're in the same room. Plus, it's totally interactive. You can all work together to make changes to a report, add slides to your presentations, even show someone how to fix their computer. Think of the time you'll save. No more driving or flying to a meeting. Plus, you can hold as many meetings as you want for one low flat rate. It's a real money saver. The next time you're waiting in line at the airport, you'll wish you could meet online instead. So sign up right now to try GoToMeeting free for 45 days. For this special offer, visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Try it free now. Okay. Now we're going to talk a little bit about near-field measurements. Maybe with antennas, it could be acoustical, it could be anything, but it's better well known in the context of antennas. Again, we're going to imagine you have some localized object somewhere emitting some sort of waves, maybe electromagnetic waves. And we're going to imagine that we can measure the excitation in some plane in front of the object. Let me draw a better plane than that. So we have some plane here. Okay, and you've got some sort of waves going through it. All right. Again, we have a localized object. We're measuring a plane in front of it. We're sampling the plane. And again, for various reasons, you want to sample closer than lambda over 2 in spacing as you scan in front of the object in the plane. And let's say you measure an amplitude AXY. Okay. Now, what we want is A of K, what the plane wave spectrum or the antenna pattern looks like in the far field, far from the object. Now, you can use the Huygens-Fresnel principle we talked about before. I'm going to use a different argument now. I'm trying to do some of this by minimizing the math. I only really want to do this in 20 minutes, so I'm going to give you an argument that's sort of similar to what we talked about last week. Imagine, instead of this object here, this localized object, imagine plane waves coming in from the backside of this. Say a particular one, some amplitude e to the I k, omega over c k hat dot r, okay? A of k hat. Well, we adjust imagine now we've measured A of xy at this point here, okay? Because of the Huygens-Fresnel principle, that point will radiate spherical waves. So in particular, it radiates the same in all directions, including the direction we're thinking about. Okay? So the component from this point to that particular plane wave that's coming through this plane is AXY, the measured excitation there, times e to the I omega over c k hat dot r. Okay? Well, you can make that same argument for every single point on this plane. Whatever the plane wave going in that direction from that point, its contribution is that times that. So the general A of k is going to be the sum over xy of AXY e to the I omega over c kxx plus kyy. There's no kz because we're going to set this plane at z equal to 0. Okay, so when we do this over that plane, that gives this number. Well, let me write that clearer. A of k hat equals sum over xy, A of xy, e to the I omega over c kxx plus k, y, y. It's actually a constant times that, but the constant we're not so worried about yet. We can calibrate out the constant later. This is looking like a two-dimensional Fourier transform. In fact, it is. It's a discrete Fourier transform, other than a constant that's not there. In fact, one can say, if you had a continuous sampling of the wave in front of it, of the plane, A of k is sum over x, y, is the integral. There's a constant up here. We're not caring about that so much. Of a of x, y, e to the I k x x plus k y y dx dy. Okay, so that's a Fourier transform of, or in this case a discrete, that case continuous Fourier transform of the distribution, of the excitation distribution in the plane in front of the source. Okay. This is a general statement about planar near field. There's used slightly different expressions for other types of near field. But it's the same general idea. It's some sort of transform, Fourier transform in this case, some sort of Fourier transform that gets you between the points in the near field and the points in the far field. Now, this function here, doing a Fourier transform of this, it's less critical on the errors, if there's slight errors in this A of x, y. Some of them are correctable. But this general technique can give you antenna patterns or even acoustic patterns for some sort of acoustic transducer like an ultrasound or something, or a sonar or some other thing. You could come out with a pattern this way. A little detail. Sometimes you don't capture all the energy with planar near field. The error caused from the fact that you're using a smaller plane is called truncation error. You're using a truncated plane. You really need a full plane to get all the energy. And again, that's only valid in the forward hemisphere. You can sort of characterize that by, after you take your scan, like eliminate all the points on the border and see how much the pattern changes, and that gives you some sort of idea of whether you've scanned far enough. But again, if you wanted the whole coverage, there's two other types of near field measurements you can do. Again, you have your localized object. If you wanted some idea of all the way around the thing, you could scan a sphere and then measure a bunch of points on that sphere close into the object, and then you can come up with what the field is in the far field. Or you could use a cylinder. That's sometimes used. You can scan a cylinder around the object. It's called cylindrical near field. That's a little bit different in some ways because you're using something called Bessel functions, but I won't get into that. That's a detail. Yeah, you can still use this to get the far field pattern. Well, what can you do with it? Back to that in a minute.
One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support.
Okay, you've done your planar near field measurement or your cylindrical or spherical near field measurement, and you've got your A of k. I was calling this the antenna pattern. It's an antenna pattern. Its square will give you something like a power pattern. There was some sort of constant in there that we haven't talked about yet. But if we wanted gain, let's say, from an antenna, we don't have gain, we just have some sort of relative amplitude of various plane waves. But what you can do is repeat the process for an isotropic radiator. You know the field for an isotropic radiator. You can compute what the field would be on the plane. That can give you the gain. Well, not quite, because you don't know any actual gains and losses in your measurement system. So what you actually end up doing is putting up an antenna you know the gain of first. And you do a scan like that. That gives you an idea of the normalization constant you need to get the gain pattern of an antenna. You can also get polarization data, that sort of thing. We're not going to go into that for anything significant, but there is an interesting application. There's some constant here times integral of a xy e to the I kx x plus ky y dx dy. Okay, that's Fourier transform. Well, one thing you can do with a Fourier transform, if you have one, is invert it. So we can now have, if we have our plane wave spectrum, and this is the A of xy on some plane, we can get A of xy for any surface, for any xy, as some constant. The constant's not important at this point. A of kx, ky, the antenna pattern, e to the I kx x plus ky y e to the minus dkx dky. Okay. This gives you the excitation that would be seen at some other point. In particular, once you have A of k and you have the object, you can compute it for points on the object. Okay, this is called, essentially in the context of antenna measurements, microwave holography, in that you're actually getting a measure of the currents that are on the antenna. Or if it's a speaker or acoustic transducer, it would be the measurements of the actual excitation, vibration amplitude at each point on the transducer. Or you might do stuff like imaging the inside of a body, like in ultrasound or some sort of diagnostic tool, or an application with circuits is you could, if you had some circuit card, let's say, and you scanned the field over the circuit card, figure out the far field pattern, project back into the circuit card, it'll give you an indication of where the currents are flowing on the circuit card and their amplitudes and phases. So this is a way without putting any type of probe on a circuit card, you can actually get currents and phases. Well, there's got to be a catch, because this sounds too simple, and it is. There is a catch. Is the inverse Fourier transform is computationally has a problem. Small errors in the plane wave spectrum lead to huge errors in the image spectrum. So you have to have a really good system to be able to do that type of measurement. We won't go into that in any more detail here, but it's a neat type of measurements to do. And if you want to learn more, we recommend for the moment this Near Field Antenna Measurements book by Dan Slater. We'll put a link to where you can get this in the show notes. It's a pretty good book that talks about the practical aspects and little details about what you need to do. Now, this week, if you're watching this podcast, I want you to open up your email client right now and send me an email at suggestions@learningmeasure.tv. Okay, I need some feedback on where you want me to go, what topics you might want me to cover. Even if you have any questions on a particular topic. It could be measurement related, it could be just general science questions, general engineering questions, anything. I want everybody who's watching this program to send me an email. Tell me what I'm doing wrong. Tell me what you'd like me to see put on this podcast. I'm still working on interviews. I want to do more interviews. I'm sure the most popular show that I've got so far is my one interview show. But let me know. I need some feedback. So get to your email client and send me an email at suggestions@learningmatters.tv right now. Okay, because I want to know what you want to do, what you want to see on this. Okay, also if you're a vendor that wants to sell a product or offer your service, or you want to be interviewed, send me an email at vendors@learningmeasure.tv. And if you want to become part of our consultant network and have some sort of role in this, and to get yourself on this podcast as an interview so you can show your wares, go to the learningmeasure.com website, join our consultant network, and then you'll be entitled to be on the podcast, and you can tell people how good you are. Okay, next week, I don't know what I'm going to do next week. Hopefully it'll be based on you guys all sending me emails, and I'll pick the topic that I think would be the most fun to do next, and I'll do that. Otherwise, I'll go in some random direction. Let me know, and I'll see you next time.